Okay, the purpose of this video is to answer a couple of questions. First is, how can we negate an implication statement? What does that look like? I mean, certainly we can write it like this, but is there a simpler way to write the negation of P implies Q? And then relatedly, is there a way that we can rewrite P implies Q without using the implies operation? We are going to be talking about logic circuits and logic gates in a few videos, and we want to see if we can rewrite P implies Q in terms of and, or, and not. So we're going to answer those two questions, and we're going to do it by looking at the truth table. The truth table, you got to understand, gives us all the information about this operation, right? There's not very much because there's only 4 different possible combinations of truth values for the 2 inputs. So this column gives us, this completely defines the operation P implies Q. So we're going to look at this to learn something about it. So what you notice here is that it's only false in one situation, which is true when P is true and Q is false. So what if we look at the negation of P implies Q? Well, the negation of P implies Q is going to have the exact opposite truth values. It's going to be false whenever P implies Q is true, and it's going to be true only when P implies Q is false, which would be just this one case. So let's look at that row, okay? The one row where the negation of P implies Q is false is the row when P is true and Q is false. So one way to isolate that row only is to say, let's require that P be true and Q be false. P is true and Q is false, which is like saying that P is true and the negation of Q would be true. I'll demonstrate that over here. If I write the negation of Q, which is going to be false, true, like that. If I put that along with P, if we combine those with and, P and the negation of Q, you can very carefully go through and do this. P and the negation of Q is true and false, which is going to be false. Then it will be true and true, which is true. Then it would be false and false, which is false. And it's going to be false and true, which is false. So we've been able to produce the exact same truth values in that column with the only true situation in the second row by this compound proposition, P and not Q. So what that's shown us is that the negation of P implies Q is equivalent to P and not Q. So that is one very useful result. Now, from that result, we should be able to obtain answer to the second question. We should be able to obtain some expression that is equivalent to P implies Q. All we've got to do is negate both sides. Remember that double negation undoes itself, right? So if we want P implies Q, that should be equivalent to negate both sides, and then we cancel the negation on the left, so we get the negation of P and not Q. And now what we want to do is try to simplify this using some of our rules. So let's pull out our reference sheet. Okay, we want to negate P and not Q. So we're trying to negate this conjunction. Now we have a rule for that. It's De Morgan's law. When you negate a conjunction, you get a disjunction, okay, so the and is going to become an or, and then we negate both parts. So this is equivalent to not P or, okay, there's De Morgan's law, not Q. And then the double negative is going to cancel out again. So this becomes not P or Q. So this was by double negative, and then this step is by De Morgan, and this is by double negative again. I'm real fast and loose with my capital letters, I guess. So there we go. So P implies Q is equivalent to not P or Q. Let's write that down. P implies Q is equivalent to not P or Q, and that is going to be another super useful it's propositional equivalence that we're going to want to use occasionally. Actually, not just occasionally, pretty frequently. So looking down here, I actually wrote those down in here at the bottom. Ignore this for now. This is going to be section 1.4. But over here we have propositional equivalences involving implication, and one of them is what I call the conditional equivalence. This is the equivalence that we use to interpret a conditional statement in terms of other operations. It's not P or Q. It's equivalent to P implies Q. So you don't have to memorize this one, okay? You don't have to memorize that. I don't have that one written down, but you can always just apply De Morgan's law to this if you want to obtain that again. De Morgan's law would undo what we just did and bring you back to here. So I've also got the contrapositive one down there and that biconditional equivalence that we talked about earlier. Yeah, those are on your reference sheet. So there you go. So those are now we've sort of established some other useful equivalences, and you've seen another example of sort of how to prove things and how to work with these